This conference will now be recorded.
Hello everyone. In coordination compounds, IUPAC rules that we have already learned. That is, what are the rules that we have to follow, and some examples we have already seen in the last class where we are having some formulas given and we have to write the name. And today we will do the reverse thing. That is, names will be given and from that we will see how we can write the formula. Okay. So the first name that we have here, for which we have to give the molecular formula, sodium. So this is the cationic part because the rule is cationic part is named first. And then monochloropentasanoferrate. And see, it is here the metal name, that is iron, it is ending with ATE. That means it is part of the anion. So the first part, that is sodium, that will be the cation, which will be present outside the coordination sphere. And inside the coordination sphere, there will be presence of iron along with the ligands. Now, if it is that is the question is arising in your mind, how many sodium atoms will be there? That also you can easily understand, because individually we don't have to mention how many counter ions are present outside the coordination sphere. So it is monochloropentasano. So there will be one Cl, and pentasano means CN5. So one chlorine and 5 cyano. Now all these ligands are ionic in nature. That is, Cl is ionic in nature, Cn is also ionic in nature. That means total negative charge that is coming from ligand, it will be -6. Okay. Now iron can have oxidation state 2 or 3, but here it is clearly mentioned it is +3. That means if it is +3 and there is total negative charge -6, outside the coordination sphere there will be 3 negative charge. And to balance this 3 negative charge, we require 3 sodium atoms. So in this way, you can easily write the formula. The second name is hexaamine iron 3 nitrate. Okay. Now see, here in the metal, you are not seeing any ATE. That means it is part of the cation. And nitrate is the counter ion, which is basically the anion. So in the coordination sphere, there will be iron and the ligands, and outside it, there will be NO3. Now iron is having oxidation state 3, that is mentioned in Roman numeral. So Fe in +3 oxidation state, and hexaamine, that means total 6 ammonia will be there. Now if ammonia is neutral, that means whatever oxidation state you have here, the outside charge that will be the same, that is 3+ charge outside. That means to balance this, you have to add 3 nitro, because each nitro is carrying -1 charge. Okay. So see, this is the formula: Na3FeClCN5 and then FeNH3 whole 6 outside the bracket. To balance 3+ charge, we have 3 nitrate, NO3 minus. Now come to the third one. Here we have amine tetra-aquo chromium 2, and it is ending with ion. That means here you do not have any counterpart, and whatever will be the charge outside the coordination sphere, it will remain there as it is. And here chromium, we are using the term chromium, it is not ending with 8. That means it is part of cation. How many ligands are there? Amine tetra-aquo. That means chromium will be associated with one ammonia, because amine, there is no dry mentioned in this name. That means only one. And tetra-aquo, that means H2O 4, because it is tetra. Okay. Now ammonia is neutral and water is also neutral. So outside we will place 2+, because here it is mentioned 2+. Number 4, it is interesting because you have platinum, which is used in 2 ways. That is platinum 2, then platinate 2. So this is actually the anionic part within coordination sphere. This is the cationic part. Okay, that is why platinum is simply platinum, but in the second term it is platinate, not platinum. Tetraamine. So Pt will be associated with 4 ammonia, close the coordination sphere. So this is the cationic coordination sphere having 2+ charge, because platinum is having 2+ charge. and amine is neutral. Then tetrachloroplatinate. Now in the second ionization sphere, coordination sphere, you will have PtCl4. Okay, here also oxidation state 2+. That means if it is 2+ and 4 chloride, that means negative charge will be outside 2-, which is completely balanced by this 2+. Overall, it is neutral. Fine. So here we have chromium, then ammonia, tetraco 2+, and PtNH3 4, PtCl4. This is 2+, this is 2-. Then up to this, is there any doubt in these 4 names how we have reached all the molecular formula starting from the name? Is there any doubt? Number 5 is potassium trioxylato-aluminate. Cation first. This is the anionic part. So that is why aluminium ending with 8. We will write potassium first. We will gradually understand what will be the number of potassium. So inside coordination sphere, trioxylato. Now oxalate is this ligand CO2-, CO2-. This is bidentate ligand. And trioxylato means total 3. And each oxalate you are getting 2 donating site. So it will be attached to aluminium like this, and 2 more site for oxalate will be there. I am writing in simple way like this. Fine. Now aluminium, it is having charge +3 and total negative charge -2 for each oxalate. So total negative charge will be -6, which is coming from ligand. So excess negative charge -3. Aluminium oxalato, it is written in simple way ox. So to balance this 3 negative charge, we have to place 3 K+, because potassium can have only one oxidation state, which is +1. Fine. And the last one, ammonium. Again, this is the cationic part. Ammonium is the anion, NH4+, just like K+ or Na+. Now we have NH4+. Then diaquo bis oxalate. Diaquo, that means 2 water. Bis oxalate, that means here you will have 2 oxalate. Now see, in the previous case we have not used tris, we have used tri, but in this case we are writing bis, not bi, not di, because we have already used di in before water ligand. So that is why bis oxalate. So there will be 2 water and 2 ox. Then it is ending with nickelate. That means nickel will be present in the anion coordination sphere. So we will write ammonium outside, and inside nickel, how many water? 2 water. How many ox? 2 ox. End it. Nickel having oxidation state 2+, and for each ox it is -2, but total oxalato 2, that means total negative charge -4. So it is +2, excess negative charge -2 outside. So you have to add 2 ammonium ion, because per ammonium ion you have charge only +1. Now look at the formula. It is same that we have written Al C2O4. This is actually oxalate. C2O4. Actually, I should write the formula, not ox like this, but sometime you will see it is also represented in this way. Right? Then nickel C2O4 whole 2, H2O whole 2. Okay, it is actually ox2. So any doubt in these 6 names? Because this type of question is very common. So if you have any doubt, you can ask me. I will repeat it once more. Now we have a problem related to this formula. Complex A, its composition is given, that is how many different number of atoms are present: 12 hydrogen, 6 oxygen, 3 chlorine, 1 chromium. This complex is treated with concentrated H2SO4, and we know concentrated H2SO4 is dehydrating agent. It attracts water, so water will be lost. That means this molecule, there is some water molecules present, that is why water is lost. So it is losing 13.5% of its original mass and it will be lost in the form of water. And how we are understanding that? It is because of this, whenever it is mentioned that there is a mass loss because of concentrated H2SO4, mostly it is because of loss of water, because concentrated H2SO4 is attracting water, it will help to remove water. Okay, now from this information you have to find the correct formula, molecular formula for this complex A. 4 different options are given, so different types of formulas may be there. And here for our convenience, atomic mass for chromium, chlorine, everything is given, and for oxygen it is 16 and for hydrogen it is 1. So from this information you can easily find out what will be the mass from this molecular formula by simple calculation. So suppose the molecular weight is X. Okay, now 13.5% of X is, just multiply 13.5 by 13.5 divided by 100. So this is the amount, suppose Y. So this is the amount which is lost, okay, of its original mass. So original mass is X, and after loss of this 13.5 and 100, that means Y gram is lost. Okay, now Y gram, it is actually the mass of water. Mass of water, but suppose there are n number of water molecules, so Y will write NH2O molecule, because we do not know what is in how many molecules. But after calculation, now you know what is the value of Y, that you can find from calculation. And once you know the value of Y and N into H2O, for one water molecule it is 18 gram. That means N into 18, that is N number of water molecules. One water molecule molar mass 18. N, if it is N moles, it will be 18 into N. That will be equal to Y gram. So from this you can easily find out what is the value of N. Okay, and you can match with this. Fine. Now another important thing that you have to understand, in the first formula you have water molecule inside the coordination sphere, but for all the other three options, 2, 3, 4, water molecules are present outside the coordination sphere. Now only the molecules that are present outside the coordination sphere, that can be removed by concentrated H2SO, not the water molecules that are present inside. Okay, that is also another important information. So if we find out the value of X, here in a different way it is done. So suppose here X is actually N, that is X moles of water. This is another way you can solve this, X moles of water. That means 18 into X, that is the mass of water, which is we have just assumed as Y gram, and this is the molecular weight of this complex, which is basically X. So it is actually Y by X into 100 equal to 13.5. This is another way of writing. You can also write it as if it is Y equal to 13.5 by 100 into X. Same thing. Okay. So whatever method you prefer. So 12 is coming from 12 water, 12 hydrogen. So 12 into 1, it is 12. Then 6 into 16, it is for 6 oxygen atoms. 35 into 2, it is for chlorine, as it is given here. And 52, that is for chromium. So this is the molecular weight of this complex. Okay. Now after calculation, you will get the value of X, which is 2. Now 2 means what? 2 water molecules will be lost, and 2 water molecules present outside the coordination sphere. It is in this case only, because option 1 it is obviously not possible, because you do not have any water molecules outside the coordination sphere. Okay, so 1 you can easily cancel, but among 2, 3, 4, here you have 3 water molecule, 1 water molecule, 2 water molecule. So the value of X, we are getting 2 moles of water. That means the last formula will be the correct formula. So is there any doubt? Should I repeat? Next problem. Oxidation state of chromium in the following complex we have to find, and this is an integer type of problem. Okay, there will be a whole number simply. Now, if you look at this complex, this is actually bridging complex. On one side, we have chromium attached with 4 water molecules. Right hand side also it is same, and we have 2 bridging ligand. Now here it is from the picture it is clear that it is peroxide. Now peroxide, it will have 2 negative charge. But when the other bridging ligand, which is written as O2. Now O2, here 2 possibilities may be there. It may be simple oxide, which is carrying no charge, 0 charge. That can act as ligand. Or it may be, sorry, it is not oxide, it is simply oxygen molecule. Right? Or it may be O2 minus, which is basically superoxide. Now when it is superoxide, it is contributing -1 charge. But when it is neutral O2 simple molecule, then it is carrying no charge. Okay. So basically by trial and error method, we have to find which one will be correct. So first you do the calculation based on, that is assuming that it is simply O2 0. Another calculation also you have to do where you will assume it as if it is superoxide. Fine. And water molecules, 4 water molecules both sides, they will have no contribution for charge because it is neutral. Okay. And chromium, mostly it has oxidation state +3 in the complex, and sometimes it is +2. Outside the coordination sphere, you have total charge, which is 4+. Okay. Now, if we are considering that it is superoxide, that is O2 minus, then total positive charge coming from each chromium, it will be +3 and into 2. That means total +6 charge coming from chromium. From peroxide, we are getting -2 charge. From superoxide, it is -1. That means outside charge should be +3. But see here it is +4. That means now if you consider it as normal oxygen, not superoxide, now here it will be simply 0. Now see +6 and -2, what you are getting +4, and it is matching with it. That means here oxidation state of chromium, when we are considering it is +3, then considering this O2 as normal oxygen molecule, dioxygen atom, diatomic O2 actually, then we are getting proper result. Fine. Sorry. So that means your oxidation state will be +3 for each chromium. Fine. And if you consider +2, suppose if it is chromium 2, in that case the calculation will be 2 into 2, that means total positive charge +4. Now from peroxide, you are getting -2 charge, and from O2, which is carrying 0, so it is nothing, adding nothing to charge, so you are getting +2. But outside C, it is 4+. That means chromium cannot have +2 oxidation state. Fine. So in this way, we can understand that oxidation state will be +3 in this complex. So is it clear? Is there any doubt? So sometimes if it is not clear from the picture whether it is simply O2 molecule or superoxide, then a different calculation you have to do, and when you will get some realistic result, that is which is possible result, then you can go for it. If excess of silver nitrate solution added to 100 ml 0.024 molar solution of this complex, the name of the complex is given, and from the name you can easily write the formula. Fine. It is asking how many moles of AgCl will be precipitated. Now first thing what we will do, we will write the molecular formula. So dichlorobis ethylene diamine. Dichloro, that means with cobalt, there will be 2 chloride like this. Bis ethylene diamine. Ethylene diamine, how we write it? En. Bis means 2 En will be there. And cobalt having charge +3. En is neutral but chloride carrying charge. So +3 from cobalt, and from chlorine it is -2 negative charge. That means outside the charge will be simply one charge. Okay, and it is ending with chloride. That means outside you have only one Cl is enough to balance this charge. So this should be the formula. Now when you are adding AgNO3 to it, the chloride that is present inside, that will not be precipitated. Only this chlorine, it will react with AgNO3, 1:1 reaction, and there will be 1 mole of AgCl precipitated. So per mole of this complex, you are getting 1 mole of AgCl. And in the question it is asking how many moles of AgCl we are getting. Fine. So it is 1:1. That is, when you have taken 1 mole of the complex, you will get 1 mole of AgCl. Now here we have taken 100 ml 0.024 molar solution. Now first thing that we will do, we will do the calculation in terms of millimole. Okay. So see, in terms of millimole, it will be simply multiply the volume in ml with molarity. So even without using calculator, you can understand. Simply we will get 2.4 millimole. But if it is 2.4 millimole, in terms of mole, now simply multiply 10 to the power -3 so that you can get mole. And what value you will get? 0.024 moles. So this is the number of moles of complex. And for each complex one, you are getting 1, so when it is 0.024 moles, obviously HCl also you will get 0.0024 moles. So that is why option C is the correct option. Is there any doubt? IUPAC name for this. So what is there in the formula? K2, inside the coordination sphere we have osmium, then 5 chloride and 1 nitrogen. Okay, IUPAC name we have to find. Now this is the cationic part, so obviously we have to write potassium first, and in all these 4 options you can find potassium. So in this cationic part we do not have any problem. Next, see this osmium that is present in anionic coordination sphere. So it must be ending with 8. Now look at all these options. Osmate, 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 osmate. So from that point of view also, all these are fine. After that, what we will do? Cl5. So total negative charge, it will be -5, that is coming from chlorine. And from for osmium, suppose it is oxidation state X. Then for each chlorine, it is -1 × 5. Okay. And total charge, if you remove 2 potassium, overall charge will be -2. Fine. Now here single nitrogen is given. When single nitrogen is given, it is basically this ion, N carrying 3 negative charge. Okay. And this is known as nitride. Okay. Try to understand the difference in different formula. See. So one nitrogen atom carrying 3 negative charge, but another anion is also there where 3 nitrogen carrying single negative charge, and it is known as azide. But in our case, it is single nitrogen atom, so it must be nitride, not azide, isn't it? So now for each nitrogen you are getting 3 negative charge. So from this you can easily find out the value of X. So 5 -5 -3, that means it is 8, -2, that means oxidation state of osmium, it will be +6. Okay. Now if it is +6, obviously this is not correct. Actually option 4 you can easily cancel out, because here there is no mention of chlorine, and also it is mentioned nitro, but simple N atom it cannot be nitro. Nitro is NO2, right? So this you can easily cancel. And now as you already obtained the oxidation state +6, so this is also not possible because here oxidation state for osmium it is mentioned +8, but +8 is the not oxidation state. Okay, +6 is the oxidation state. So among 2 and 3, which one will be correct? So try to understand the difference. Potassium, it is same. Osmate 6, this is also same. Pentachloro, that is also same. So where is the difference? It is mentioned azido. Here it is mentioned nitrido. But we do not have azide because it is not N3 minus charge. It is N3 minus charge. So it will be nitride. That means this will be the correct option, not option 2, option 3. So is there any doubt? One example of nitride and azide also I can show you. For example, when we say sodium azide, the formula is NaN3. That means it is Na plus cation, N3 minus ion. Similarly, if you want to see example of nitride, for example, aluminium nitride. So here the cation is Al3 plus and the anion is nitrogen carrying 3 negative charge. Okay. I hope it is clear now. Should I repeat it once more? Why option 3 is correct? Is it clear? The correct IUPAC name for Mn3 CO whole 12. So here we have 12 carbon monoxide ligand. Now carbon monoxide is neutral and it will have no contribution for charge. So C, option C, you can find that here manganic, that means charge for manganese given 2. Okay, but it cannot be 2 because CO is neutral and the molecule, that is the carbonyl complex, it is overall neutral. So there cannot be any oxidation state for Mn. It is simply zero oxidation state. Now if C is cancelled, among ABC, in all cases it is zero oxidation state. But the important thing is here we do not have any cation or anion, right? But manganese, that is the name of the metal, that will be written first. Name of the ligands, that will be written first because the rule is such. We always write the names of the ligands first and then we write the name of the cation. Metal. Because here we do not have any cation. It is simply manganese zero oxidation state. That means if it is not anion, it will not be ending with 8. So this is also not correct because here it is ending with manganate. But that cannot be correct. And dodecacarbonyl, that is fine because dodeca means 12. Fine. Just take simple example. Octa means what? 8. Hepta means 7. Then similarly, when it is dodeca, it is 12. So dodecacarbonyl, that is absolutely correct. That is also present in option C. But in option C, it is ending with manganic. But this type of term we do not use, and also oxidation state mentioned +2, which is not possible. C is cancelled. B is also cancelled because it is dodecacarbonyl manganate, but it cannot be manganate. Now we are stuck between A and D. What is the difference between A and D? In A, manganese is written first, then dodecyl carbonyl, but here it is dodecacarbonyl first and then mention trimanganese. So which option will be correct? It is the last option. And this is the structure of the molecule. As you can see here, Mn, Mn, Mn. So these two CO, they are common for both these Mn. And these right hands, if I am marking 1, 2, 3, manganese 1, it is carrying 3 CO. Manganese 3, that is also carrying 3 CO. Manganese 2 is carrying 4 CO. 4, 3, 3. And these two CO that are common for these 1 and 3 manganese. But all these details you don't have to know. Here just for your, if someone is curious, I have given this picture so that you can understand how it actually looks like. Because here you have 3 metal center. This type of complex we have not seen until now. So this is the first example we are seeing here. So how it looks, that important for us to know. But to answer this question, you don't have to, even if you don't have any idea about the structure, that is fine. Okay. So option D is the correct option. Here we have total 4 statement: S1, S2, S3 and S4. Okay. Now in option A, B, C, D, you can see F means false and T means true. That means if you choose option A, it means basically the first statement is false and statement 2, 3, 4, these three are correct. Okay. So which of this combination will be correct, that we have to find. Okay. The question is clear. First you have to understand the question first, otherwise you will make some mistake. Okay. So the first statement is saying that IUPAC name of this compound is pentaamine thiocyanate N chromate 3 tetrachlorozincate. This part is cationic, right? This part is anionic. So it is ending with zincate, that is fine. But see here the first part, pentaamine, okay, NCS. Now NCS, it can be written, suppose there is any metal and then you are writing NCS, or there is metal you are writing SCl. So these two are having different meaning. When you are writing S first, basically it is associated with metal through sulfur because it is ambidentate ligand. It can interact with metal from both sides. So if you are writing sulfur first, that means it is interacting through sulfur, not through nitrogen. When it is interacting through sulfur, the name is thiocyanate, and when it is interacting through nitrogen, then it is having different name, which is isothiocyanate. But here it is mentioned thiocyanate, so this cannot be correct. Another information is also wrong here. It is mentioned chromate, but chromium here it cannot be 8. Correct? So all these are indicating in this part it is okay, but here two error is there. It is not thiocyanate, and then it is also mentioned N. But if it is isothiocyanate, then only you can write N, because it is interacting through N. Then we write N, but it is written thiocyanate. That means it is interacting through sulfur, but still mention capital N, which is not possible. So the first statement is not correct. Okay. Now the second statement. Is it clear why the first statement is not correct? Any doubt? Second statement, more salt, formula given. It is an example of double salt. Remember in the first class I have mentioned that under molecular or addition compound, two categories are present. One is coordination compound, another one is double salt. So double salt example, there we have also seen more salt was there. So this is actually an example of double salt, and this is true. Third statement, in CONH3 whole 4 NO2 whole 2 NO3, coordination number of cobalt is 6. So it is very easy to understand, because within coordination sphere, cobalt is attached to it 4 ammonia, 2 nitro, and all these are monodentate ligands. So simply add these two numbers, coordination number is 6. So this is true. The last one, in FeCO5, secondary valency of iron is 0. Now there are two types of valency, remember, primary valency and secondary valency, right? Now here, if we consider oxidation state of iron, this is actually 0, because CO is neutral. Outside coordination sphere you do not have any charge. So here 0 oxidation state, that is actually the primary valency, and coordination number is 5, that is the secondary valency. But secondary valency of iron is not 0. So this is also false. So all these are mentioned here. So for statement 1, if you want to know the actual correct name, it will be pentaamine isothiocyanate chromium, not chromate. Oxidation state +3. Now +3, one NCS carrying negative charge, so outside the charge 3 plus balanced by -1 charge, outside it will be -2 only, sorry, +2. And ZnCl4, Zn is having oxidation state 2, so +2, 4 negative from chlorine, so it will be -2 charge outside, so it is balanced. So the cationic part will be pentamine isothiocyanate chromium 3, then tetrachlorozincate. Actually in this part there is nothing error, but there is error in the cationic part. So this is not correct. Then the second statement is true, that we have already seen, that is more salt example. Statement 3, here cobalt is bonded by sigma bond with 6 monodentate ligands, so this is also true. And primary valency is 0, not secondary valency. And what is secondary valency, primary valency, that we have already discussed under the topic name important terms, important terminologies. Okay, so it is F, T, T, F. Okay, so option C will be the correct option. Any doubt?
No, ma'am.
Now after finishing nomenclature, next important topic under this chapter is isomerism, and the questions are very frequent from this topic. Okay, compounds that have same chemical formula but different structural arrangement, they are called isomer. That is the general definition of isomer, and the phenomena is known as isomerism. Okay, so if you are finding two molecules having same formula but there are different structural arrangement, you will call these two molecules, their relationship between them is they are isomer to each other, and the process is isomerism. Now because of this different arrangement of atoms, they will differ in one or more physical or chemical properties also. Okay, so there is direct effect of this different structural arrangement both on physical property as well as chemical property. Okay, now what type of isomerism we can find in coordination compounds, we will see. But before that, look at this flow chart, and this flow chart is only for coordination compound, not that is because isomerism you can also find in organic chemistry, but that is completely different. Here we will see especially for coordination compounds. So when we are talking about isomerism, the first two possibilities are structural isomerism and stereoisomerism. Now stereoisomerism, from the term you can understand, it is all about spatial arrangement, and it arises because of the difference in spatial orientation of the ligands around the metal. So here connectivity, that is bonding connectivity, will be same, but when you are considering the orientation in three-dimensional space, there will be difference. And under this stereoisomerism, we can have geometrical isomerism. In short, it is mentioned as GI, or it will be optical isomerism. Come to this side, it is when it is structural isomerism, which is arising because of difference in the structure. So now bonding connectivity may not be same. Okay, unlike stereoisomerism. And under structural isomerism, we have total 4 categories: ionization, hydration, linkage, coordination. Okay, the first thing that we will see is the left hand side, that is structural isomerism. So what is structural isomerism? It arises because of difference in chemical linkages. That means bonding connectivity will not be same, and distribution of ligands within and outside the coordination sphere. Now this thing is completely new. It is applicable only for coordination compounds, because this term coordination sphere is applicable only for coordination compounds. This type of thing you will not find in organic compounds, right? So when there is a coordination sphere we are talking about, so and there are species both outside and inside. Okay, so depending on they can change their places. The outside moiety can come inside, the inside moiety can go outside. So depending on this distribution of ligands outside, inside of the coordination sphere, we can have different possibilities and different linkages. Okay, so main thing is here bonding pattern is not same, bonding connectivity is not same. Okay, so these are the common points which is applicable for all these 4 types: ionization, hydration, linkage, and coordination. Fine. The first one, ionization. So here I'm writing 1. So when it is ionization, just focus on this term. You will get easily the idea what it actually means. So ionization means what? Coordination complex. When it is ionizing, you are getting some cationic species, some anionic species. But if two compounds, they are related to each other by ionization isomerism, obviously it means that after their ionization, the species that you are getting, there will be difference. So that is why the name is ionization isomers. So it is the result of the exchange of groups or ions between the coordinating sphere and the ionization sphere. So when we write any molecule, suppose Ml6 and outside also there is L prime, basically it is coordination sphere and this is ionic sphere. Fine. So just to look at this example, here we have cationic sphere and this is ionic sphere. Platinum, 2 chlorine, 4 ammonia, 1 sulfate. Here also same thing, 1 sulfate, 4 ammonia, 2 chlorine. So number of atoms it will be same because that is the basic definition of isomer. But how they are different, that is the important thing. Here you have 2 chlorine and 4 ammonia inside the coordination sphere, and in ionic sphere you have sulfate. But in the second example, now sulfate is coming inside and the 2 chloride they are going outside. Okay, in both cases the outside moiety is carrying 2 negative charge, sulfate is carrying 2 minus charge, Cl2 total negative charge also minus 2. So basically if you ionize the first one, what you will get? You will get Pt, Cl2, NH3 whole 4, 2 plus ion, and SO4 2 minus ion. But if you are ionizing this, what you will get? You will get Pt, SO4, 4 ammonia, 2 plus, and 2 chloride. So after ionization, the species cationic and anion species that you are getting, they are not same. So that is why they are ionization isomer. Now, only this type of isomerism is possible only in those compounds where the counter ions can act as potential ligand. The meaning of this statement is, suppose you have sulfate outside, okay? Now it can also behave as ligand, but it is the case that the outside the group that is present, it cannot behave as ligand, then it cannot go inside, because if something is going inside the coordination sphere, that must act as ligand, otherwise it cannot enter inside the coordination sphere. Okay, so only when the counter ions can act as ligands, then only this type of isomerism possible, because now it is going inside and the inside ligands coming outside. Fine. Now if we look at the second example, see, cobalt is attached with 2 chlorine, 4 ammonia. Outside there is NO2. NO2 is carrying minus 1 charge. That means here we have charge plus 1. So this is the cation you will get, and the anion you will get NO2 minus. But look at the second one now. What is the difference? Now NO2 is going inside and one of the chlorine is coming outside. Now negative charge is also same. Positive charge is also same. So now after ionization, what you will get? You will get this cation and you will get different anion, Cl minus. So different cation and anion you are getting. And the third example, Pt attached with 2 hydroxy 4 ammonia. Ionic sphere we have sulfate, but in the second example, 2 hydroxide coming outside, 2 HO minus coming outside, sulfate going inside. Okay, so in both cases, coordination sphere is carrying 2 plus charge and SO4 is carrying minus 2 charge. Here also total negative charge minus 2. So these are the examples of ionization isomers. I hope it is clear, or is there any doubt? This is the first type under structural isomerism. Some more information related to this ionization isomerism. See, example, we have taken cobalt, bromine, NH3 5, 2 plus charge balanced by SO4. Name is pentaamine, bromo, cobalt 3. So here charge is 3 plus, 1 negative ligand, Bn minus. So outside charge is 2 plus, and sulfate. So when it is ionized, you are getting this type of cation, and this is the N. Okay, and its ionic ionization isomer, that is the second example. See, the color is also different because, as I have mentioned, physical properties will change. This is red violet, but this is simply red. Now the name is pentaamine sulfato-cobalt 3 bromide ion outside the coordination sphere. And now you are getting this cation. Anion is different. Now look at this information. A is forming white precipitate with BaSO4. So this is A. When you are adding with BaCl2, that means you are adding BaCl2 to this solution, which is carrying Ba2 plus ion. So Ba2 plus ion, when it will come in contact with SO4 2 minus, it will form BaSO4 precipitate. BaSO4 with barium sulfate, it is highly insoluble, so it will be precipitate. Okay, and if it is B, obviously it will not react with BaCl2. Okay, similarly, now B, what it can do, if now you are adding AgNO3 to it, that means you are basically adding Ag plus. So in presence of Ag plus, now it will form AgBr in the form of precipitate because it is also not soluble. Okay, but A on the other hand doesn't react with AgNO3 because silver sulfate, that type of compound is not formed. So precipitate, when you get, when some compound is there which is not soluble, if it is soluble, then you cannot get precipitate, right? So there must be some insoluble salt formation, and only BaSO4 and AgBr, these two are insoluble salt. Okay, so this type of information may be given in the question, and it will be asked that identify the complex from this information. Okay, after ionization isomerism, next we will go to hydrate isomerism. Look at this flow chart. Hydration isomerism, the second one. But before going to hydration isomerism, some initial information we must have. So let's see that in a complex compound, when water molecules are present, it can remain in two ways. Water molecules which are behaving as ligand, they will be coordinated with the metal ion. So they are part of the complex. So they will be inside the coordination sphere. MH2 whole X inside third bracket. But if the water molecules are act as water of crystallization, not ligand, now they will appear outside the coordination sphere. Try to understand the difference. When they are outside, they are not behaving as ligand, they are known as water of crystallization. But when they are inside, they are basically acting as ligand. Okay. Now, hydration isomerism, you can find some similarity with ionization isomerism, because here also you will see H2 is going inside and some species which is inside coming out. So you may think that what is the difference with ionization isomerism? But actually there is difference, because in ionization isomerism, the species that are exchanging their places both can act as ligand. But here H2O, when it is present outside, it is actually not ligand. It is water of crystallization. So that is why there is a different terminology we are now using, which is hydrate isomerism. Sometimes it is also called solvate isomerism. Basically, hydrate, the word is originated from the water, hydration, water. And solvate, it is generated from solvation. That means except water, there may be any other solvent also. Suppose you have taken alcohol, and alcohol molecules are inside and outside. So the more general term is solvate isomerism, but mostly it is water. So that is why you will find this term more common. So this isomerism, it occurs because of different number of water molecules as ligand when they are inside the sphere. and as water of crystallization when they are outside the coordination sphere, and they are known as hydrate isomers. Now these isomers, they are special case of ionization isomerism. As I have said that you can find some similarity, but it is one of the type of as if ionization isomerism, but it is not considered under ionization. It is completely different. Okay. So in this case, water molecules, or it may be solvent. So when it is solvent, you will call it solvent isomerism, not hydrate. Suppose if instead of water there is alcohol, then it will be solvent isomerism. Okay. In which water molecules or solvent inside and outside the sphere exchanged. Example, this is the formula. Chromium 6 water 3 chloride. But now different possibilities for formulas. See, 3 possible hydrate isomers. In the first example, which is violet in color, all the 6 water they are inside. That means they are acting as ligand. Fine. So this is the first one, number 1. All the water molecules are neutral, so chromium, the charge oxidation state, that is present outside. And this 3 plus is balanced by 3 chloride. Now the second one, when one water molecule outside and one chlorine is going inside, color is different. Now see, one OH2 replaced by Cl, and charge is also now 2 plus, and outside there will be 2 Cl minus 1 water. And the third one, now we have 4 water molecule, 2 chlorine, 2 chloride, and here we have 1 chloride, 2 water molecule. So now another water molecule also replaced by Cl, and see, the more Cl is going inside, positive charge is also reduced, and that has to be. So color is different. This is number 1, this is number 2, this is number 3. The first one violet, then blue green, and the last one dark. So all these examples are clear. Any doubt?
No, ma'am.
Next we have linkage isomerism. This is the third type under structural isomerism. So this type of isomerism, it is possible only with ambidentate ligand. And we know already what is ambidentate ligand. The ligand which can attach with metal through 2 different atoms. Okay. So this type of isomerism arises when ambidentate ligand is bonded to the central metal atom or ion through either of its 2 different donor atoms. Now, this isomerism can exist only when ambidentate ligand is present. So suppose some molecule is given and it is asked that try to find out whether linkage isomerism possible or not. Just carefully observe and see there is any ambidentate ligand present or not. Because if it is not present, no question of linkage isomerism. Their presence must be there. Here we have some examples of ambidentate ligands. Cyano, it can coordinate with metal through CN or through nitrogen. Then NO2, it can attach with metal through oxygen or through N. Okay, so these are the different examples. And these isomers you can differentiate by IR spectroscopy, because in IR spectroscopy, just take this example. Here you have metal carbon bond, but here you have metal nitrogen bond. And for different bond, obviously the stretching frequency will be different. So in this way, if these two are given, if you are doing IR spectroscopy experiment, you can easily understand these 2 compounds. You can identify these 2. So look at this example. Cobalt attached with 5 ammonia and 1 NO2. So this is the formula 5 NO2. Charge is 2 plus. Because NO2 is carrying -1 charge, this is 3 plus, outside 2 plus. And this is yellow in color. And the other one, that is red color. And what is the difference? See, now this is attached through nitrogen, but now it is through oxygen. So that is why the color is also different. So the red isomer, remember, it is thermodynamically unstable. So that is why if you are keeping this red one, what will happen? Gradually, it will slowly convert to the yellow isomer. And if you are heating it, then it will quickly convert to the yellow because it is thermodynamically more stable. So if there is any equilibrium, it will be more towards the yellow form. Okay. Another example, cobalt attached with 5 ammonia, but now it is through sulfur interacting. In the second one, it is through nitrogen, that is it. This is thiocyanate, this is isothiocyanate, these two. Rest of the isomerism we will see in the next class. So regarding all the slides, if there is any doubt, please mention. So we are ending the session here. Thank you for listening.